Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to Easy Learn, and this is the continued topic relevant to the previous ninth episode. In the ninth episode, we are trying to discuss the force on a conductor that carries an electric current. This is a conductor. For example, it is connected with the electrical source in the presence of a constant magnetic field. Then it will experience a force either in this direction or this direction perpendicular to the direction of the field, but this is the overall force that is experienced by the conductor that carries the current. Basically, this current is carried out with inside this conductor there are the flow of electrons or the flow of positive charges in case of the conventional current. And what happens to the each single charge that flows in the inside the conductor, and either the force also exert and have any impact on either single charge, or just have an overall effect on this conductor. And now we are going to consider single charge in the today's episode, and basically it is relevant to the previous episode, but in this sense we are going to separate and further enhance our knowledge and going to discuss deep details of this conductor. And today's task is, a current is however only a stream of the charged particles. What is current? First, defining the current, that is the stream of charged particle and they are moving inside the conductor, and of course this will produce a current. The force is exerted on the charges themselves, so the force is also exerted on the charges, basically the moving electrons that make up the electric current. Charge, what is charge? Charge is basically the moving electrons. These are the moving electrons that make up the electric current. I tried to show up in this second or third slide of the episode 9 an animation of the charges. So this is the electrons that make up the electric current. Hence it should be possible to derive an expression for the force on each charge, and this is the basically expression F is equals to ILB, and this is the expression for the force on the current carrying conductor, and this is the same case we are trying to apply on the theta is equals to 90 degree in this case, and it for the maximum, because sine theta is maximum on 90 degree, sine 90 is equals to 1 and sine 0 is equals to 0, we must have at least 90 degree angle, at least 1 degree angle for minimum experience of for the minimum force experience, and maximum 90 degree for the ultimate experience of the force. We found that the magnitude of the force on the conductor was given by this equation, that is the same and nothing changed in this equation. Consider a small charge q. This is the small charge q. It is moving perpendicular to the magnetic field B, and this is the as applied at 90 degree with the velocity v. Here if we are going to compare it with the previous episode, here it is the basically the direction of the current, while here in this case it is replaced with the direction of the velocity. Velocity is basically the movement and the direction in which the charge tries to move. So this is the direction of the velocity of the, it is now going to take this position that is represented by the dotted lines in the next couple of seconds. Okay, so it is called velocity. And what is the total distance covered by this charge? That is called the length. And now we are going to consider this. In the previous case the total length is the length of the conductor, and here length is length which the charge travels some distance, it is taken as length, and the time that it consumes is also taking into consider, moving it in time t, the time it takes for the charge q to pass through a point. And the what is I is the same. What is b is same. I is not same, b is same, I is replaced with v, L is what I already explained. From the definition, what is current? Current is basically the flow of the charges, that is charge mean q, with respect to some time. So q by t from the definition. And what is the definition of the velocity? Velocity is basically the distance covered by somebody, something like a charge in our case, distance covered by charge in a unit time. Let's suppose this is the unit time and taking as t, and what is the distance? That is L over t, and by just rearranging L is equals to Vt, V is going towards the other side and multiplied with the t, so t is going to the other side and multiplied by V, and L is equals to Vt. The force on this small charge is given by F is equals to ILB, and now we are going to substitute the value of I, that is Q over T here, and also substitute the value of L, that is Vt, multiplied by B. F is equals to VBQ, because T is cancelled out with this. So the vectorial equation of this, F is also a vector quantity, V and B are also vector quantity. V cross B dot Q, the direction of the force is given by the right hand rule, same as the case. The force on the charge Q moving with velocity V at angle theta, but the difference here, it is in the previous case we have the I, and we have the magnetic field intensity, magnetic field, and I. So we are taking into consider the angle theta with the I with B. Now I is replaced by the V velocity, so we are trying to consider the angle theta with I, because I is replaced with V, so V versus magnetic field B. This is the angle between these. Are the magnetic field intensity is right now in our case cross, shows that it is inside into the screen. So point out your fingers of the right hand into the screen, and you will notice that this magnetic field, this is into the page, and your thumb must be towards the direction of the velocity, and then the palm will represent the direction of the force, and in our case the A, it is definitely upward. You can try it by yourself. And this is the case of the positive charge. Positive charge mean that it is for conventional charges, that in the conventional current that starts moving, that is due to the flow of positive charges. If we are going to discuss the other thing, that is electronic current basically means that the flow of negative charges are due to electron, and its direction is from negative to positive, while from positive to negative, it means that it is the conventional current, or so with all the formulas, in the episode 2 or 1 I explained that we discuss here, it is just applies, or right hand rule or right hand grip rule applies on conventional current. If you are going to change this with the electronic current or negative, it means that you are trying to adopt the electronic charges, electronic current, so these formulas are not valid for them anymore. Anything right now, if you try to use this or question appears in exams, then just follow the instructions and do opposite direction of the answer what you found by right hand rule. Okay, direction is in this our B case is outside the screen, so point out your finger outside the screen, and the thumb must be towards this velocity, and if your thumb must be pointing towards the velocity and fingers are out of the screen, pointing out of the screen, then definitely your palm is downward. But in case of the electronic charges, you are trying to just do the opposite here. In this case of the force, just replace this arrow with the opposite side as here, so this is the right direction. And again, this is the electronic charges, and F is equals to VBQ, and here in this case C, this is positive charge. It means that we are following again the conventional current, and when you are following the conventional current, it means that the direction here, why F is 0, because the angle between the force, magnetic field, and V is 0, and we are sine 0 0, so it must be noted that for any sort of the force experience on the charges, there must be 90 degree for the maximum case. Suppose there is some angle but not 90, not 0. Suppose that these yellow arrows represent the magnetic force, and it is towards this direction, and the velocity is at this direction. and this is not represented here. It is a positive charge or negative. If it is not represent, definitely consider it is as a negative charge. We are sorry, consider it as a positive charge, because we have made formulas for our positive charges, so consider it as a positive charge. Anyway, this is the velocity v, and there is an angle theta. It must be at angle 90 degree perpendicular, as I drawn. And if it was like that, then there is an angle of the 90 degree, and sine 90 it is 1, and there is a maximum force that can be experienced outside of the paper. Because just point out, according to the right hand rule, point out the fingers in the direction of the B magnetic field, and your thumb must be in direction of the velocity, and then this is the your palm, and I had represented with the help of dot. It means that it is out of the screen, the way or to represent the 3D pictures. And suppose that we are facing a strong magnetic field and a constant strong magnetic field, and a small charge experience a constant velocity. Then what happens? It will try to adopt this path, that is the circular motion. How this happens? Just suppose that this is the m, any charge, any mass, negative charge, and it is just trying to move in this direction with the constant v, but a strong magnetic field is applied. Then a strong force will be experienced, and it is applied at a right angle. So according to the right hand rule, this is a negative charge, so also take into consider. Put your fingers into the according to the right hand rule, into the screen, the direction into the screen, and your velocity must be towards the right, and the direction your palm will try to show and point into the direction upside, but this is negative charge, so do opposite, and its direction is this, downward. So because the force is here downward, velocity is all pointing out this side, then it will try to change a little bit and adopting this circular path. If we consider other couple of other examples too, like this one, but time is short, you can consider these by yourself. And I just want to show you here, this is the radius, and this only happens when it's strong and a constant. In ideal cases, it is useful in the practical oscillator or other applications, I don't know, but because this is not our topic right now, I just try to this is just an extra thing right now. What I just want to show you here is this, so try to focus this. When a current flows through a conductor in a magnetic field, as you know what we discussed, when a current flows through the conductor in a magnetic field, the force causes the conductor to move at right angle to the direction of the current if it is free to do so. This is what we discussed in episode 9. This is a summary of episode 9. When the current flows through the conductor in a magnetic field and it is free to move, but the force is basically at the right angle to the direction of the current, and it is free to do so. And what if the conductor is fixed and it is not free to move? The force moves free charges. Then there are free charges. Suppose this is the conductor, magnetic field lines are into the page, according to just for the understanding, into the page, and it is constant. I just connect here positive charge and negative charge. Just try to point out according to the direction of the this is the direction of the current, and it is from positive to negative. Suppose that your fingers are just into this paper, and I is the direction of the current. Your thumb must be in the direction of the current, and then what? This is the direction of the force. But if it is fixed, the conductor is not moving anywhere, I just try to fix this conductor, then what? This is the direction of this is the terminal where I just applied some charges. This is the one terminal for the positive sake, and this is the other terminal I used for the negative one, and then these two sides are left uncharged or just empty, and I'm not connected anything here. Then charges are forcing themselves, and they are just taking the position because they are the free charges. Actually the flow of the charges makes the current, and they are trying to align themselves in opposite polarities here, for example positive here, negative here, and there is if we attach the galvanometer here, then we will of course experience some force here, sorry some current or voltage here, that is called potential difference. It means that if it is fixed only, if it moves, then this will not occur. The result is a small potential difference between the sides of the conductor. This effect is known as Hall effect. This the taking of the position according to the opposite polarities here and develop some potential difference here. This is called Hall effect. It's most noticeable in this semiconductor material that can be used to detect and measure the strength of the field. It is named after the Edwin Herbert Hall, complete name, and Hall effect is named after him. This is the demonstration of this Hall effect, and if it is connected with the external source here, this is the external source applied, positive negative, and this is the width of this conductor, length, and this is the height. We are not interested in the conductor height, length, width, just trying to show you that if this is the external current is applied and magnetic field direction is upward, it is not shown here, but suppose it is applied, then what, these two terminals are used, these two sides are used as a terminals for the positive and negative sides applied from the external source of the current connected here. So these two sides are empty. In the center of these two sides we can use to attach the galvanometer here for seeing the deflection of the voltage and see what's the scenario here. Here it is the deflection, and this is the actual demonstration of Hall effect. When this is a piece of the conductor and magnetic field is constantly applied, and suppose that we current starts flowing, it will experience a force and it is fixed. We are not allowing the conducting material to go anywhere in anywhere direction. So what does it happen if we just try to get and connect these two terminals with the galvanometer? We can see that what happens, we will experience a force, that is a force of charges, because charges align up on the opposite ends, and it is some voltage obtained, and this is called potential difference. So I think this is enough for today's episode, for today's lecture. We will try to continue this introduction to electronics in the coming lectures too. So take care. Allah Hafiz.